So for this session, we'll continue working on the technology aspect of producer theory, and we're going to be building more indicators for thinking about a firm's technology, leading up to the next session. So the next time we will be talking about specific examples, specific production functions, like the Cobb-Douglas, like a linear production function, and so on. But today we're going to keep things still more broad and more general. Even when we get to the situation where we're analyzing production functions and that f function takes a specific functional form, it's still abstract, right? It's still like the exponents or the coefficients might be alpha or beta, right? We're not going to necessarily put numbers on those, but at least we're heading to a point where we're going to be talking about production functions and putting some sort of structure into them. So, okay, I'll go through and start today by the concept of returns to scale. So this should be something that you have heard about before. In some cases, people loosely talk about returns of scale. Other times you hear the term of economies of scale. Economies of scale are going to be a related topic to this one, but we need to bring in the cost consideration before we talk about economies, right? So right now we haven't talked about cost at all. So we're still in the production process, technological change type of things. So the question here for returns to scale is the following. So how does output respond to increases in all inputs together? That is what we're thinking about, is scaling up inputs, all of them simultaneously, and thus returns to scale. So how does the output respond? That would be the returns to increases in all inputs together. That would be the scale of the inputs, right? So returns to scale. So that is scaling up all inputs simultaneously. So that concept has a specific sort of definition, and I'm going to just write it out. And you'll see that there is 3 specific cases of returns to scale. So I'm going to say that given a production function that essentially maps points from the positive Rn space, right? Because you could have n inputs, and maps them into the positive R space, right? These are going to be the units of output that the firm is producing, and we're talking about one output, so that's the deal here. And also having x belong in the positive space of real numbers. One, we can talk about constant returns to scale. These are going to be symbolized as CRS. So a lot of times you're just going to see CRS automatically talking about returns to scale. If for all t greater than 1, so you have a parameter here that takes the value of greater than 1, not 1, but numbers greater than 1, you see that the f of is equal to t times f of x. So essentially, what does that say? If you multiply all of your inputs by t, that's going to give a value of f, that's a production level, that is going to be equal to the production level that you would get by taking that t and multiplying it with the original production function where you have not scaled up your inputs, right? So if t here is 2, the output that you get from 2 times x, double the amount of, let's say, capital and labor, is going to be equal to 2 times your original production function of 1 times x. That's the idea of constant returns to scale. The second case, now you can imagine the increasing and decreasing aspect to this. So you would have increasing returns to scale. That would be IRS in short, if, again, for all t greater than 1, the output that you get from this scaling up of the inputs now is greater than what you would have had if you multiplied your original production function by this factor t. So here, the output that you would be getting by scaling up the inputs, let's say by 2 times x, that would lead to a specific level of output. That output is going to be greater than 2 times the original production function where you haven't scaled up the inputs. So the last case should be very easy to write. So you would have essentially constant, increasing, and here we're going to talk about decreasing returns to scale. DRS, if for all t greater than 1, the output that you're going to get from t times x is going to be less than t times f of x. And that completes the formal presentation of returns to scale. This is a very important concept in many ways for economic theory, because a lot of modeling has happened with the assumption of constant returns to scale at the level of firms or economies, while a lot of other folks suggest that we should be modeling the world through increasing returns to scale. These are some discussions that have been happening for several decades now, and the more you advance in terms of thinking about economic theory across different parts of economics, the more you see models that involve also increasing returns scale. But you'll see within our microeconomics course how these assumptions play a role for the variety of models that we are exploring. So that's all on the definitions for returns to scale. The other related concept that I'm going to bring up here is the one of homogeneous functions, or homogeneous, depending on your pronunciation. So I'm going to start with the definition here. A function f, again showing the mapping, it's pretty standard in our case, is called homogeneous of a particular degree, and we're going to say of degree k for all t, some parameter greater than 0. What happens? The f of tx is equal to t to the power of k times f of x. So this one, you'll see how that applies in our case. But essentially, it says that it's homogeneity or that feature of these functions that have a degree k suggests that if you scale up the inputs, right, if you scale up those x's by a particular amount, and here we just assume that t is greater than 0. Obviously, it covers all of these situations that relate to returns to scale, but also a different range for values for t. You're going to get the output of f of t times x being equal to t to the power of k times this original, let's say, production function. So let's see perhaps an example here. So the example could be let function f of x1, x2 arguments. You can consider those as inputs, but this applies for things that are not also production functions too, right? Is equal to x1 to the power of 2 times x2 to the power of 3. And the question here is show that it is a homogeneous function of degree 5. How would you do that? Well, you can go to the definition, obviously, and say, well, if we multiply the inputs by t, we should be getting that t raised to the power of 5 times the original production function, right? If that would be the case. So let's go ahead and do that. What does it mean to multiply inputs by, or rather scale up both of the inputs by t? How would we write this form? tx1 and tx2, okay? And that means that when you transfer that t into the functional form, what happens?
Parentheses tx1 squared times parentheses tx2 squared.
Not squared, the second one?
To the third, sorry.
To the power of 3. That's the functional form, which means that this square can be spread out, right? This can be written as t to the power of 2, x1 to the power of 2, t to the power of 3, x2 to the power of 3. And that also means that you can pull the t's together, right? You have the same base. So this is going to be t to the power of 2 plus 3, x1 to the power of 2, x2 to the power of 3. So you see what has happened here, right? So you have resulted to t to the power of 5, and then you have x1 squared times x2 to the power of 3, which is this expression over here, right? So I can take this part and just write it as my original f function, right? So f of x1 comma x2. So this is the result. We scaled up the production function or a function by a factor t. You say we doubled it, we tripled it. That's typical. You increased it by 10 times, whatever that t is. It doesn't really matter. All that matters is that we have figured out that eventually that output of doubling, let's say that these amounts of inputs, is going to result to the original output that we would have had before we did anything to the size, to the amount that we're using for the inputs, multiplied by t to the power of 5. So we are effectively showing, according to our definition, that this function is homogeneous of degree 5 because it simply follows that particular pattern. Does that make sense? So I will say that generally speaking, I'm going to say here, note 1. So generally, if you have a general form of this production function with one input raised to one power and another input raised to another power, we can write this as, let's say, f of x1 comma x2 is equal to x1 to whatever power, let's say alpha, and x2 raised to whatever power, let's call that beta. Then it is a function homogeneous or a homogeneous function of degree alpha plus beta. Even more generally, if your f of x doesn't only have two inputs, it has n inputs. You have x1 beta 1 times x2 beta 2 times dot xn to the power of beta n. Then, this is a homogeneous function of degree. What would be the degree here? Beta 1 plus beta 2 plus dot 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 plus beta n. Or if you can use your summation signs, right? I is equal 1 to n of beta I. You don't want to be confused by this, but essentially you take all of these exponents, you add them up, and you find the degree of homogeneity of the function. In some applications that you have already perhaps worked on, in consumer theory, you've done that. In the cases where you had the Cobb-Douglas production form, right? So you would say f of k comma l is equal to whatever parameter times k to the power of 0.5 times L to the power of 0.5. Actually, that stops here. How do you sort of figure out whether this is a homogeneous function? It has the format that we have established, right? You have the arguments of the production entered multiplicatively. You could have a parameter here that whatever else is part of the functional form doesn't matter. What it matters is if these are entered multiplicatively and what is the power to which the inputs are being raised. So in this case, that would be a homogeneous function of degree 1. This is important because of what I'm going to write here for note 2. The first part involves something that happens in the case of constant returns to scale production functions. So we're going to say that constant returns to scale production functions are homogeneous of degree 1 and vice versa. Production functions that are homogeneous of degree 1 exhibit constant returns to scale. The point here is this function over here. we can start from the understanding that it's a homogeneous function and we're representing a production process. That means that you have a function that is a constant returns to scale. So that's an important finding. So very quickly you can judge constant returns to scale over here. There is two more things to consider. So I'm going to write the vice versa over here, that production functions that are homogeneous of degree 1 exhibit constant returns to scale. So we like these functions for making some assumptions with regards to returns to scale. We also have the case for increasing returns to scale. So here we're going to say that production functions that are homogeneous of degree k greater than 1 exhibit increasing returns to scale. But not all increasing returns to scale functions are homogeneous of a degree of k greater than 1, right? So this is essentially a special case. This is essentially what we're talking about. So the use of the Cobb-Douglas production function and similar functions to this one, right? So here, for example, if I made this a function that is homogeneous of degree of k greater than 1, what would I do? Give me one alternative production function to this example of the Cobb-Douglas.
Just go A times capital times labor.
Yes, because the powers would be 1 plus 1, that would be 2, right? Your k would be 2. So production functions that are homogeneous of degree k greater than 1 exhibit increasing returns to scale. So it's a very easy way by using these types of functions to say, oh, you have increasing returns to scale. Oh, you have constant returns to scale, or decreasing returns to scale. So I'm just going to write the third one just to have a complete example or a complete discussion here. Oh, I'm going to say that converse is not true over here. And production functions, sorry, I'll make sure it's visible, that are homogeneous of degree of k less than 1 exhibit decreasing returns to scale. So you had the case here for the discussion for constant returns, increasing and decreasing returns to scale.
Sorry, so when you say the converse is not true, you mean production functions that have increasing returns to scale, that exhibit increasing returns to scale, do not necessarily have a degree.
They're not necessarily homogeneous of degree k greater than 1. Meaning you could have other functional forms that do not follow that particular formatting of these functions, that we have this particular form over here. Does that make sense? So this is a sort of a specialized sort of version. What was the question?
I think I was making a comment that,
and that's why you see them a lot in your homeworks and in a variety of applications. You see them in economic growth theory. You see them in a lot of places. So everything that we do here also applies to other areas of economics. So if you ever wanted to study some economic growth models at the macro or the regional level, you would be using these types of functions. So let me also show you, let me visualize that. That's okay. But I should be able to see the screen, right? This seems to be stuck, but it's okay. Oh, there we go. Perhaps some time lag. The other thing I want to show you is visualizing returns to scale. And I'm going to show you the example of constant returns to scale and increasing returns to scale. So figures on returns to scale. So let's start first with constant returns to scale. How do you visualize those? Again, two inputs for our examples. So two axes, capital on the vertical axis, labor on the horizontal axis. Let's start with an isoquant that we're going to label as 100. That'll be your Q, right? That will be the number of output, how much output you're producing. And let's say that this is the point of producing 100 units of output with worker, 1 unit of labor, however the unit is defined. and 1 unit of capital. Worker with a laptop producing 100 units of the good. Let's say you are going to explore the situation where t is equal to 2. That means that you're going to look at f of 2x, which you expect under constant returns to scale to be 2 times the f of x. Yes? So essentially, all of this is saying is that if you double the inputs, you go here and you say, oh, here's a second worker. Now you have 2 workers, the same scale here, 2 units of capital. What do? Your dotted line going up, do the dotted line horizontally. You find that point over here, right? So you know that every point in this diagram of capital and labor has an isoquant passing through it, right? It's the same thing as sort of the indifference curve map. So you know that there is an isoquant that passes through this. Let's say this is the shape of the isoquant. If we have assumed constant returns to scale, if this is the production function that we are employing, let's say this was a Cobb-Douglas, what is going to be the Q over here? 200. So the same thing would happen. I don't have the space over here to draw this, but if I went to 3 units of labor, 3 units of capital, I would be able to find another point, and I would know that on that point you have an isoquant passing that represents an output level of 300. Make sense? Okay, pretty straightforward. So now let's see the alternative example of, let's say, increasing returns to scale. Very similar sort of diagram here. So, okay, let's say we do something similar. Let's put 1 unit of labor here, 1 unit of capital here. Oops. And you have a point, and you have an isoquant passing through that point, and you symbolize it as such. And in particular, so if t is equal to 2, then you're going to get an expression that says that f of 2 times x, when you've doubled your inputs, has to be more than 2 times your original output. Let's say this output was 100. So here we don't have a specific functional form to get the exact number, so we're going to we'll define some numbers. So let's say this is 2 workers and 2 units of capital. Okay, we are going to find that point. In order for us to have increasing returns to scale at that point, what do we want? We want that output, whatever the number of units is, to be greater than 2 times the original output of, let's say, 100. So we want this to be more than 2 times that output. What could we do here? We could call this...
Would you just write it greater than 200? Or would you put a specific quantity, 201 or 210?
You would have to put a specific quantity that eventually would be emerging from your specific functional form, right? What if we say that this is 400? That satisfies our definition, right? So in this particular case, I would say actually you would have an f of 2x being equal to now 4 times 2 to the power of 2 f of x, homogeneous of degree 2, I would say, right? What if we did t is equal to 3? Okay. Here for the constant returns scale, just for completeness, if t was equal to 3, f of 3x would be equal to 3 times f of x. Over here, we want to have f of 3x being greater than 3 times f of x, correct? According to our definitions of increasing returns to scale. So let's say you have 3 workers, 3 units of capital. You find that point in the capital labor space. There is an isoquant passing through this. What we do know, in principle, in order to have increasing returns to scale, is that you have to have an output of more than 300 units. What if we had an output of 900 units over here? Yes, you have increasing returns to scale, right? But you have a specific type of increasing returns to scale. So here, actually, given the numbers that we decided on, the F value when you triple the amount of inputs that you're using is going to be 3 to the power of 2 of f of x, right? And now you know why this is happening, right? You have this functional form that is homogeneous of a specific degree that is greater than 1. So this is sort of the behavior. So this is how you symbolize effectively returns to scale by using our sort of contour map, our level set of our production function, this cross section at different levels of output. So if you visualize it, or if you try to plot something like this on a computer for increasing returns to scale, you have sort of this functional three-dimensional surface that increases smoothly. For constant returns to scale, for increasing returns to scale, you have the amount of output rising sort of exponentially on that surface, right? So that's the idea. When we get to thinking about specific production functions, I will bring some computer generated output so that we can look at how these functional forms look like in 3D also. But really, you don't need the three-dimensional representation for doing any analysis. Here, as you will see, we play a lot with isoquants and their slopes and sort of this notion of capital to labor ratio. Yeah. Any questions, anything that we should be discussing up to this point?
I had a question relating to the homework. One of the questions asked for a couple different isoquants, and I believe that we just went in and did the slope for those isoquants. Were you wanting something like a visual of those as well, or were you wanting the slope?
If it's asking, if a question generally asks for the marginal rate of technical substitution, I would like to see a calculation. But if you find that you can express, let's say, capital as a function of labor, and you pin Q down to a specific value, then you have an isoquant that you can also plot, right? So if you want to visualize the isoquant, you need to do two things. Solve for K, right? K as a function of L gives you a line in this space, but you also need to pinpoint Q, right? You need to make Q equal to a specific value, and then you have this function over here, for example. So you can plot those things.
I think they're generalized a little bit, so I was doing just
A set value of Q is going to allow you to plot things like this.
That's what I was. I think so.
Cool. So let's see, what else should we talk about? As a reminder, so for constant returns to scale, production function, comma L of K, T times L is equal to T F of K, comma L. So that means that F of K, comma L is homogeneous of degree 1. There is a well-known calculus theorem that suggests that if you have a function f that is homogeneous of degree k, then the first order partial derivatives are homogeneous of degree k minus 1. So what are the first order partial derivatives? If it's a production function, we're talking about the marginal products being homogeneous of degree k minus 1. So essentially what we're saying here is if you have a constant return scale production function like the Cobb-Douglas that's homogeneous of degree 1, the functions for the marginal products are expected to be homogeneous of degree 0, which means that you multiply the inputs by t raised to the power of 0 for homogeneous. So degree 0, that becomes 1. So essentially, you don't have effects on the marginal product as you're scaling up outputs, if you can conceptualize it. But we're going to work out through the equation so that you can see how that works. So I'm going to write it out. So from calculus, function f, is homogeneous of degree k. Then its first order partial derivatives are homogeneous of degree k minus 1. So we have our standard degree k homogeneous functions. We take partial derivatives, and you get functions that are homogeneous of degree k minus 1. Well, how does that work out? So here I'm going to say the math. So for, let's say, an f of tx1 all the way to txn being equal to t to the k of fx1 to xn, okay, that should be convincing us that we have a function that is homogeneous of degree k. Then if we take the first order partial derivatives and we do that on both sides, we should be arriving at something that says that the partial derivative of this function with respect to an input is homogeneous of degree k minus 1. Right? That's simply what we're trying to find. So let's say partial derivatives from this expression. So del of ftx with respect to a specific input or argument in the function is going to be equal to the partial derivative, because they're the same thing on both sides, right? The partial derivatives of the right-hand side with respect to xi. So how do we take these derivatives? For this side, we have to apply the chain rule. The other side is a little bit easier to apply the derivative. So on the first side, you have del xi. That's what we're taking the derivative with respect of this functional form here, f of tx1 all the way to txn, multiplied by what is in the expression inside the f function, right? Which is the derivative with respect to xi of txi. This is a chain rule application here. We need that. On the other side, over here, with respect to this derivative, you have t to the power of k. That can come outside of the derivative calculation. And then what remains is the derivative of this functional form where the arguments have not been multiplied by t, right, with respect to xi. So that's a simple derivative, right? You don't need the chain rule over here. Over here, you needed the chain rule because you have altered the arguments inside the function. So you have a function inside the function, right? You have an f of g of x, effectively. That's why we use the chain rule here. Here you don't need to do anything. This is the derivative of the f of x with respect to xi. So del I of f of x1 all the way to xn. Fantastic. This is an equation that we're going to manipulate effectively. So what do we have here? What is this? This is an expression t times xi. We take the derivative with respect to xi. What remains is t, correct? So this is going to be simply t. This is a derivative that we can't necessarily do anything with at this point. One sec. Thank you for letting me know. So nothing happens here, right? So this is the derivative that we took with respect to xi that gave us t. Over here, del xi, nothing happens, right? We can't do anything with this expression. You simply have the scaled up production function. On the right side, we still have the same thing. T to the power of k times del xi x1 to xn. So nothing happened between these two lines. We simply translated this derivative into what we know that it is, t. Now the next step and last step is to divide by t. Because we want to get it out of the picture over here, we simply want to have this partial derivative. So we're going to say xi of f of tx1 txn is equal to, if we divide by t, that t goes away, right? T divided by t on the left-hand side. T to the power of k divided by t is t to the k minus 1. So we divide by t on both sides, k minus 1. And then the derivative stays the same. Del over del xi of f x1 all the way to xn. So this is helpful because we learned something here. And what we learn, I say, is that del of f, del xi, is homogeneous of degree k minus 1. Why? Because we're looking at the derivative of this function here, of our production function. Essentially, we're looking at the marginal product of labor, the marginal product of capital, whatever. We can set that, and when we take that marginal product and we multiply the inputs, right, we're doing this scaling up of all of the inputs simultaneously, right? And we're going to look at the marginal product of one of those inputs. We figure out that this is going to be equal to the original marginal product. How much was my marginal product before you scaled up the production process by increasing all of the inputs by a specific amount, multiplied by this parameter t scale raised to the power of k minus 1. This is essentially the definition of a homogeneous function, right? Don't be confused by the fact that you have a partial derivative here. This is a function, right? This is a function of all of the inputs. We just, instead of having the total product function, we're looking at the marginal product function. Hey, again, the storyline is you look at the marginal products when you've scaled up capital, labor, all of the inputs. What does this equal to after doing a little bit of calculus? That is equal to the old marginal product, that's it, multiplied by that factor t that you raised the inputs by twice, 3 times, 10 times, however many times, raised to the power of k minus 1. Okay? That translates to this. So when you have the production function being homogeneous of degree k, the first order partial derivative, that is the partial product, the marginal product, is going to be homogeneous of degree k minus 1. Let's put this into something that is going to make more sense so that you can see what the application is here. Okay, so I'm going to say that this implies that the marginal products, how do we symbolize the marginal products? F subscript L. Okay, we're comfortable with that notation. Are homogeneous of degree what? If the original production function is homogeneous of degree 1, what are the marginal products going to be homogeneous? Degree what? 0, k minus 1, right? Degree 0. Why is this important? Why am I bothering you with all of this today? Let's write it out. So you have the marginal product of, let's say, labor is equal to F subscript L, notation-wise, which is equal to del L, like the derivative with respect to labor of the production function, like K L. That is going to be equal, by definition, by the fact that this is a function that is homogeneous of degree 0 to this expression. Del over del L, that's the marginal product of the production function when I have scaled up the inputs. For example, this is equal to del L of F of 2K 2L. So the marginal product that I'm getting in this production function is going to be the same marginal product that I'm going to get if I simultaneously doubled the capital and I doubled the labor, or tripled it. The same marginal product for both labor and capital, if you want to expand this to capital too. This is important for a very specific reason. So we're going to piggyback on this one and set, let's say, t equal to 1 over L. As I said, this applies to all cases. These properties of homogeneous functions apply to all cases of t being greater than 0. So why don't we set t equals to 1 over L so that we can see what happens. So if you do this, the marginal product of labor is going to be equal to F of L. Remember, this is a function of capital and labor, right? So don't get confused by thinking that the marginal product is a specific number. It's, in general terms, it's expressed as a function of the variables that you have in the mix. So think about the Cobb-Douglas production function. What happens when you take a partial derivative with respect to one of the arguments? It's a function of all of the arguments, right? So this one is going to be equal to f subscript L, the partial derivative with respect to labor of TL. Because we've set T equal to 1 over L, if we put it in this expression, this is going to be K multiplied by 1 over L. That's going to be K over L, right? And then this one is going to be T is 1 over L times L. That's going to be 1. Now, when you have a functional form with one of the arguments becoming a constant, that's not an argument anymore in the production function, right? So in this functional form, if one of the arguments has become 1, we can express this as a single argument function, K over L. So, important finding. The marginal products, that's going to be the marginal product of labor, the marginal product of capital, only depend on the capital to labor ratio. In this particular type of a production function, when you have homogeneous function of degree 1, right? These are production functions, just generally for functions of degree 1. So partly why the assumption of constant returns to scale is important, and so this assumption of homogeneous functions of degree 1, because you arrive at a situation where the marginal products of labor and capital only depend on the relative use of capital and labor in production, not their absolute level. If it's low levels of labor, it's the ratio between them. So in a lot of modeling, the capital to labor ratio becomes very important quantity, right? So automatically you have these functional forms, f of k comma L, and very quickly people start writing things out as functions of capital to labor ratios, right? So they combine those measurements. So I would say depend on the capital to labor ratio, not on absolute levels of K and L used. The other cool thing that you learn from this is the MRT behavior now. How did we define the MRTS? We defined it as the ratio of the two marginal products. Well, if each of these marginal products are only a function of the capital to labor ratio, what would be their ratio a function of? Again, the capital to labor ratio, right? So it's like when we put them together in an expression and each of them depend on the capital to labor ratio, the MRTS as a whole is simply going to depend on the capital to labor ratio. Yes? So only depends on the ratio of K over L. So we started with homogeneous functions of degree 1. We like those, constant returns to scale. We look at the marginal products, homogeneous of degree 0. Why do we care? Because that means that if they are homogeneous of degree 0, each of these marginal products only depends on the ratio of capital and labor, not the absolute amounts of capital and the amount of labor in the calculation, right? Fantastic. That means that if this happens for labor and this happens for capital, and because those two things define the marginal rate of technical substitution, the marginal rate of technical substitution now only depends on the ratio of capital to labor. And I'm going to show you a picture so that you can understand why this is actually important. So here is the picture. So I'm going to do this diagrammatically. I'm going to say, look at array, let's say the isoquant space and a array from the origin. So let's look at K and L, right? And let's look at array from the origin, and it doesn't matter which one you're going to pick. Array from the origin is simply a line from the 0, 0 point outwards, and I'm just going to pick the 45 degree angle. What is happening to the ratio of K and over L along this array? It stays the same, right? So K over L stays constant along the ray. So if this is the 45-degree line, right? So you have 1 unit of capital, 1 unit of labor, right? 2 units, assuming that the scale is the same in the axis. 2 units of capital, 2 units of labor. So the K over L is equal to 1. If you have an array that is higher, that's 2 to 1 or 3 to 1. And if it's lower, the reverse, right? So that's great. Let's look at the slope of then I would say the slope of a firm's isoquants is the same at any point along the ray, since we have this relationship between MRTS and the capital to labor ratio, be a function of K over L. K over L does not change, so MRTS we expect is not going to change either. So let's redraw this. Capital labor, 45-degree angle. That's your K over L over here. So you would expect that your isoquants are going to have the same slope along this ray. So every isoquant that comes through is going to have the same slope along the ray. Okay, we will see what this actually means for a process of production next time. But this is what we have sort of figured out based on some of our considerations of homogeneous functions of degree 1.